take a calculator, it could be any calculator, and plug in your favorite number. For me, that'll be 67. And what I want you to do is take the cosine of that. Then take the cosine of the resulting number. Then take the cosine of that. And then just keep taking successive cosines over and over and over again. And what you may find is that the number that shows up in the calculator converges to some value around 0.739. And that's not actually a coincidence. That's actually displaying a very well-documented phenomenon in the field of dynamical systems. So, I'm not going to be covering the exact phenomenon in this video, but maybe a later video in the series. What I want you to take away from this is that dynamical systems is quite an interesting field with a ton of real-world applications. And this series in particular is going to be explaining dynamical systems and applying these principles to learning, or rather machine learning algorithms. And why is this relevant? Well, machine learning is freaking everywhere. If you've ever used ChatGPT, Gemini, Claude, or what have you, then you've used machine learning algorithms. And so have hundreds of millions of users daily. So knowing the mathematical foundations of machine learning, whether that's through dynamical systems or another field, it can help inform the design of more efficient and more effective algorithms in the future. And given that there's so many people using these algorithms, this could make a pretty big impact. Anyways, time for the boring stuff. So the cosine thing from earlier is an example of a dynamical system. And a dynamical system informally is just a set of equations that describe how a system changes over time. Now, formally, it has three components: a state space, a time set, and an evolution operator. I'll define what both of those are through examples. So, X, the state space, it's the set of all possible states that a system can take. And so, for example, in the cosine example, the system that we were using, it was a calculator, and the calculator can occupy any real number. So really, the state space is the entire real number, or the real line, okay? So pretty straightforward. Now, the time set, t, is the set of all times that the system occupies. So this one's a bit trickier, but essentially what we were doing was we started off with something like 67, then we took the cosine of that. Then the term 2 would be cosine of 67. And so really the time that we were using, it was 0, 1, 2. So in our case, in the calculator example, our time set, the set of all times that we occupied, it was just a bunch of integers. Okay, specifically, that's the set of positive integers union 0. Okay. Now we have the evolution operator, which is a function that tells you how your system changes over time. That's the actual equation that's governing everything. So in our system, we have that every term is the cosine of the previous term. So we could express this, like so. F of x of n is equal to x of n plus 1. And what is f? Well, it's cosine. It's the cosine operator. Okay? So f is basically just our update rule. We call it a map or update rule. And one interesting thing that I would like to note is that the time set, it's not always a set of integers. It oftentimes is. That we call those, when the time set is a set of integers like this, we call that a discrete time dynamical system, because, you know, the time is evolving in jumps of one. Discrete. Now, there's also the case where time is a continuum. So for example, like we have from 0 to 5 seconds going continuously. Say we have like a car that's moving at 10 miles per hour for 5 seconds. Well, that's a continuous time dynamical system, because it's not like the car is bunny hopping every second. No, it's moving smoothly and continuously. So that's continuous time. But in this series, we only talk about the discrete case. And I'll explain this why later in the series. Suppose that I deposit $100 into the bank. There's a 5% annual interest policy, and we are recording the balance on January 1st of each year. What is the dynamical system? Well, we need to define the state space, the time set, and the evolution operator. So the state space is pretty obvious because you can have any real number amount of dollars in the bank. You could have $1,000, you could be 5,023 cents in debt, so that's negative 5,023 cents. Okay, so then our state space is just R, the real number line. Pretty straightforward, okay? Now, since we're recording balance on January 1st of each year, we're really concerned with beginning of year beginning of year 0, beginning of year 1, beginning of year 2, and so on. These are discrete time steps. So really, we're concerned with times 0, 1, 2, and so on. This is the positive integers and 0. Pretty straightforward. Now, because we're worried about these discrete time steps, this is a discrete time dynamical system, and in those, we can define an update rule or a map. And in this case, since we have 5% annual interest, each term n plus 1 is only defined in terms of the nth term. So, sorry, what do I mean by that? Well, I mean that when defining the relationship between the n plus 1th term and the previous terms, we really only need to be concerned with the nth term. So, for example, time step 2 is going to have 5% more money than time step 1, and likewise, the n plus 1th term is going to be 5% more, or 1.05 times x of n. In dynamical systems, we often talk about orbits, and so what is an orbit, at least in the discrete case? Well, it basically means that we just set an initial condition, or a 0th term, in the sequence, and then we just iterate it a bunch of times. And the orbit is just the whole set of all the iterates. Seems pretty straightforward. So in our example 1, we had 67 as the initial condition, and then we took the cosine of that. That's the first term. The second term is cosine of 67, and so that would mean that the orbit is just 67, and then cosine of 67, and so on. You get it, right? And interestingly enough, we talked about this before, but it converges to some value around 0.739 and so on. And so when it converges to a real number, this is what we call a converging orbit. Now, in the other example, where we had, a principal investment of $100, and then the next term was 105, and then you get the idea. You can probably guess that this is going to go to positive infinity as the time goes to infinity, because there's nothing bounding it from above, nothing stopping it from continuing to increase. And so we call this a diverging orbit. In this video, I introduced dynamical systems theory and some important vocabulary terms that we'll use later. And if you're interested in reinforcing the concepts learned in this video, then please check out the free tutorial that I have linked in the description.